Welcome to your Intro to Statistics, Unit 4, Lesson 2. Yesterday we talked about random variables in general. Today we're going to talk about a specific kind. We're going to talk about binomial random variables. And we will learn how to determine the probability of events modeled by binomial distributions. So what are binomial probabilities? Probabilities associated with binomial or Bernoulli experiments where there are two possible outcomes for each trial, and we're trying to count the number of successes in a certain number of trials. So the first feature, the thing that you check for to see if you want to use binomial distribution, is that there's a fixed number of trials, and we denote the number of trials by the letter n. The n trials need to be independent and repeated under identical conditions. And each trial has only two outcomes, or you can define it such that there's two outcomes: success denoted by S and failure denoted by F. One thing you need to know is that success is not always a good thing. It's just what we're looking for. So success could be a good thing. It could be a basketball player making a shot. It could be a not such a good thing like a light bulb being defective. It just means successfully having the characteristic of interest. For each individual trial, the probability of success is the same, and we call the probability of success little p, and the probability of failure is little q. Since you only have two choices, success or failure, p and q have to add to be 1, or once you know p, you can figure out q by doing 1 minus p. The central problem is to find the probability of x successes out of n trials. So let's say you have 20 trials and maybe you want to know the probability of having 12 successes. That's what we're looking for. So again, binomial experiments have repeated independent trials. The number of trials is equal to little n. There are two outcomes per trial: success, S, and failure, F. The number of successes is X, the probability of success is P, and the probability of failure is Q, or 1 minus P. Okay, so let's look at an example and see if it's a binomial experiment. A marksman takes 8 shots at a target. He normally hits the target 70% of the time. Find the probability that he hits the target exactly 6 times. So let's see if it's a binomial experiment by checking the characteristics. Okay, and again, we want to make sure there's repeated independent trials. The number of trials is n. We've got to be able to define success and failure. There has to be a number of successes that we're interested in, X. The probability of success has to stay the same throughout, which is P, and the probability of failure does too, and Q equals 1 minus P. So let's look. So what is success and what is failure? Well, in this case, we're interested in find the probability that he hits the target exactly 6 times. So success is what we're interested in counting there, or finding the probability of happening a certain number of times. So hitting the target is the success. So the failure is not hitting the target. Let's see what the probability of success is and then determine the probability of failure. Well, it says he normally hits the target 70% of the time. That's the probability of an individual success, so it's 0.7, which means the probability of failure is 1 minus 0.7, which is 0.3. In this experiment, there are n equals, let's see, he takes 8 shots, so 8 trials. So X is going to be the number of successes he has, so X in this case is going to be 6. Find the probability that he hits the target exactly 6 times out of those 8 shots. So X is 6. All right, now here's the formula. You'll be given the formula. I'm also going to show you how to do this on the calculator. Either way you want to do it is fine. If you're going to choose to use the formula, you got to be able to use it. You don't have to memorize it, but you have to be able to use it. All right. Remember we did combinations, and we could do the number of combinations when you have n trials and chosen from the n objects. Actually, it's n objects, and you had x that were chosen. So that's what we would do here. It's also called the binomial coefficient. And remember, it's equal to n factorial over x factorial over n minus x factorial. And so you're welcome to use that. And then we do times p to the x, because there's x successes, and then q to the n minus x because there's n minus x failures. So what you have is the probability of getting so many successes and so many failures, and then the number of orderings of those successes and failures among the n trials. Okay, so here's the formula all spelled out, and here it is with just the combinations notation there. So n is the number of trials, p is the probability of success, q is 1 minus p, or the probability of failure on each trial, and x is the number of successes. So calculating this, when we are given that n is 6 and p is equal to 0.1, we're going to find the probability of getting 4 out of those 6 as successes. So this isn't the marksman problem. This is just a little baby example to help us use the formula. Okay, so it's n factorial, so 6 factorial over x factorial, so 4 factorial, times n minus x, so 6 minus 4 factorial, times p to the x power, so 0.1 to the 4th power, q, which would be 1 minus 0.1, which is 0.9, to the n minus x power, so 6 minus 4 is 2, and so that's going to give you 15 for your number of combinations, and 0.0001, because that's 0.1 to the 4th power, 0.9 to the 2nd power is 0.81, and you multiply it all together, and it's 0.001215. So let's go back to our marksman situation and actually find the probability here. So n is 8, p is 0.7, and we're going to find p of 6. We're going to find the probability of getting 6 targets that are shot. Okay, he actually gets the target 6 times, and out of 8. So the probability of getting 6 is going to be 8 factorial over 6 factorial over 2 factorial. Where did the 2 come from? That's the n minus x, so 8 minus 2. Okay, and then 0.7 to the 6th power, because we've got 6 successes, and then q is 0.3 to the 8 minus 6, so 2nd power. And so that's going to give you 28 times 0.117649 times 0.09, which gives you 0.2964755. So about 30% of the time he'll get 6 hits out of 8 shots. Okay, using your calculator, using your CAS on this is wonderful. You want to go to your scratch pad. Okay, so it's just the calculator scratch pad. So you're going to go to your menu and choose probability. And under probability, one of your options is distributions, and you're going to pick binomial PDF. X is the number of successes. Okay, and so it's often written as binomial PDF NPX. So for this case, you're going to enter 8 for N, P for 0.7. Okay, it says X is optional. You want to do that, or else it gives you a whole list of things. So 6, and you get the same thing. So round to 3 decimal places, so 0.296. All right, so let's practice again. Make sure you get out your calculator and actually do this. Try it with n equals 8. Individual success is 0.25. We want to find the probability of getting 6 successes out of 8 trials when the probability of success is just 0.25. And so that comes to 3 decimal places is 0.004. So go ahead, stop the video if you need to, and do this with your calculator to make sure you've got the keystrokes down. Okay, welcome back. Let's look at several cases here. Suppose the probability that a certain treatment cures a patient is 0.3. So individual success of being cured is 0.3. 12 randomly selected patients are given the treatment. So what's n? That's right, n is 12. So we're going to find the probability that A, exactly 4 are cured. So X would be, 4. All 12 are cured. So X would be, you got it, 12. None are cured. So that's going to be X equals 0. That would be sad. Now the last one here is kind of interesting. At least 6 are cured. And we'll talk about what X is going to be in just a second. Okay, so exactly 4 are cured. This is part A. So N is 12. X is 4. The probability of being cured is 0.3. So the probability of not being cured would be 1 minus 0.3, which is 0.7. So we can just put this in our calculator, binomial PDF 12.34, and we get 0.231. Okay, so there's about a 23% chance that 4 of the 12 will get cured. Okay, what about all are cured? That would be awesome if all 12 are cured, but there's only a 30% chance that each individual is cured, so I don't think this is going to be very likely. So n is 12, x is also 12, because we're saying all of them are cured. The probability for an individual being cured is 0.3. Probability an individual will not be cured is 0.7. So we do binomial PDF, and it's going to be 12 for n, 0.3, and then 12 for x. And that turns out to 3 decimal places to be 0. So it's not going to happen. None are cured. Okay, well that would be really sad. Nobody gets cured. So n is 12, x is 0, because we're not saying anybody gets cured. P is still 0.3, q is still 0.7. So we do binomial PDF, 12.30. So that comes out to be 0.014. So at least that's really unlikely, and it's 1.4%. At least 6 are cured. What would x be? N is still 12. P is still 0.3. Q is still 0.7. But what is x? At least 6 means 6 or 7 or 8 or 9 or 10, 11 or 12. So one thing you could do is go through and just with your calculator, find P of 6, P of 7, P of 8, P of 9, P of 10, P11, P12, and get all those values, just going back through and using your calculator over and over, and then adding them up, and you get 0.117. But it sure seems like the calculator should be able to do that for us, and it can. All right, you can go to Menu Probability and try Binomial CDF, okay, CDF. And for this, you do N, P, and then lowest x, biggest x. So you would do binomial CDF, not PDF, CDF, 12.3, 6 to 12. Okay? And boom. Press enter. Actually, get your calculator and do this. Go ahead. Pause me. I'll wait. Okay. So you should get 0.117 just boom. Doing that. Pretty cool, huh? Your calculator is an amazing thing. All right. Thank you again for your attention and for taking good notes. Go ahead and try to do the problems to try on your own. We'll go over them in class. Remember, you have to have them done to get full credit. I will see you in class. I hope you have a great day.